Hello and welcome. This is going to be the first video in a series that attempts to help understand operations research. Operations research is, of course, also called management science, and it was designed or created as a means to best design and operate a system. A system is a series of interdependent components that work together to accomplish a goal. Many of these systems are defined by mathematical models, which serve as representations of real-world scenarios. The first type of model we will be looking at is called a prescriptive model, which looks to maximize or minimize the objective function. A fun fact about operations research is that it was actually first called this during World War II by the British military. The British asked scientists to best allocate resources and analyze military problems. Now we're going to look at the three aspects of a prescriptive or optimization model. First, we have the objective function, which is the model's need to either maximize or minimize a certain value. In most circumstances, you're going to be maximizing profit or minimizing the cost to make a certain good. Another example of this would be to maximize number of vehicles at an intersection. The next in the prescriptive model is the decision variable. Decision variables are values or variables under our control. And these controllable values influence the performance of the system. Therefore, it's our control influencing the system. A couple examples of this would be X being the number of trucks allowed at the intersection, and Y being the number of cars allowed at an intersection. And finally, we have our constraints. Our constraints are restrictions of the decision variables, which make the optimization function or prescriptive model feasible. Examples could be that trucks can never exceed more than 7 vehicles at the intersection. Another would be that cars can never exceed 9 vehicles at the intersection. And finally, the number of cars with the number of trucks can never exceed 14 total vehicles. This would serve as a bound for this optimization model, which would allow you to maximize the number of vehicles by satisfying these 3 constraints with these 2 decision variables. Now we're going to go and look at another example. Here we can see a bakery currently sells Rice Krispies for $1.50. It sells brownies for $2 and cookies for $1. It costs 50 cents to make brownies, 35 cents to make Rice Krispies, and 25 cents to make cookies. The inventory in the store allows for only 35 baked goods at a time. The amount of brownies can never exceed the number of cookies combined with the number of Rice Krispies. Maximize the profit of this bakery. So as you can see, I went through and I underlined anything that I thought could be seen as important as either a constraint, which I will mark the constraints in blue now, or a decision variable, which I will highlight in green, and the actual objective function, which I'll highlight in purple. Now we can start with our objective function. The objective function clearly is stated in this problem. It will not always be given so clearly, but it's useful for a very basic situation. So our objective function is to maximize profit. Now we are going to later define what profit is equal to, but now we are going to go to the decision variables. And we are going to define these. Now you can clearly see that I've highlighted brownies, Rice Krispies, and cookies. So we're going to have R represent the number of Rice Krispies made. So clearly the number of Rice Krispies made is under the control of the bakery itself. The cost is not under your control, but the number sold is. So now we're going to define B as the number of brownies made. And then now we are also going to define X as the number of cookies made. So now we've defined the three things under the control of the bakery, the 3 baked goods. Now we also need to know that these 3 baked goods cannot at the moment define what profit is. We need another 2 decision variables. So now we are going to go with S being the number of cells made, and C being cost of making the baked goods. So now we have our profit defined. The final step in this example is to create the constraint, or the constraints, plural. As we can clearly see, the sales are equal to the number of Rice Krispies made or sold times the price plus 2 times the number of brownies plus 1 times the number of cookies. Now we're also going to define cost as cost to make the Rice Krispies is 35 cents times the number of Rice Krispies made plus the cost to make brownies times the number of brownies made plus the cost to make cookies times the number of cookies made. This has now defined our sales and our costs. So now we can go back up to our profit being P and set that equal to our sales minus our costs. That's going to be what we are maximizing. Now we are going to look at the other two underlined in green, blue. The number of the inventory of the store only allows for 35 baked goods at a time. So now we're going to do R plus B plus X must always be less than or equal to 35. And the amount of brownies can never exceed the number of cookies combined with the number of Rice Krispies. This now defines the two other constraints, being inventory and the, the baked goods constraint. And now a third constraint, which will be later discussed in another video, is the non-negativity, but all variables B, R, X, S, and C all need to be greater than 0. If you allow any of these to be negative, it creates a very terrible situation. So non-negative. Thank you for watching, and I hope you'll watch the next video.